Okay, this video is about rotational equilibrium. What does it mean? Well, equilibrium in the past, when things weren't rotational, always meant that the sum of the forces equals zero. And that's true when things don't rotate. Like you got a box here, and if it's going to stay at equilibrium, then all the forces on all the sides have to be equal, right? If there's F1 and F2, then F1 has to equal F2. Well, that's not enough if stuff rotates. You also have to have the sum of the torques equal to zero. And that gets to be kind of a tricky deal for some of these problems. And we're going to see how come that's a tricky deal. Now, where do we take the torque from? Because again, we know that torque is R cross F, or for our purposes really RF sine theta, because we're never going to use it really as a cross product, at least in terms of the three-dimensionality of a cross product. We're really just going to solve for what the actual value is. Okay, and this is just the magnitude of it. And we're always calling it either counterclockwise or clockwise. So the trick is, where do you take the torque from? What is the pivot point? And that's actually a thing that you get to decide in some problems, like the point of pivot. So like we're going to look at those. So okay, you choose a convenient point. As long as it's a point that could be a fulcrum. In other words, a point where the actual, if it's a lever that we're talking about, like a bar with like sitting on the edge of two things, you can use this as the, you can use that point, or you can choose this point, or you can choose that point. It doesn't matter which one you use, as long as you're consistent which one you choose. Okay, that's the key part. So we're going to look at two specific examples to get a good feel for how this works. The first one is the sign hung on the wall. It's a classic. So we've got a wall here, and we've got some sort of a sign. Like we've got a rope here. And it can be a weight or something like that. Usually it's sometimes like a sign. And then there's like some sort of a beam here. There's a flexible point here. Or maybe it's like attached to the wall. Maybe it's not. This is a string. And then there's some kind of sign or something like that here. Sometimes it'd be a weight off the end. It doesn't make a difference. And this there'll be a beam here. It has a mass of little m. The sign will have a mass of big M, okay, and we got massless stuff here. So there's an obvious rotation point here to measure the pivot from, and that's this thing here. So when you have this kind, some of the things you're going to solve for are the tension on this thing, the force of tension. You're also going to want to solve for what is the horizontal force, like on the pivot, and what is the vertical force on the pivot? Is the pivot holding it up or not? Those are some of the things you can solve for, or may have to solve for. And they'll be balanceable forces too. So first, we got to find the sum of the forces. And these are the forces actually on the rod, because that's the rotating body. Okay, that's the thing that can rotate. It seems weird to think about the idea of that object rotating, but it can. So what are the forces? There's going to be some theta here. And again, there's going to be in the x direction. There's going to be a horizontal force. Looks like pushing to the right. And there's going to be some t cosine theta force that way. And again, if it's at equilibrium, they got to add up to zero. And as far as the y, there's a lot of things that are going to act on it. There's going to be the vertical force, t sine of theta. And then maybe maybe this is positive. I don't know. If I get a negative answer, then I know that it's actually pulling down on it. Okay. And then we're going to have minus little mg and minus big mg. And all that's going to equal 0. Sometimes they'll tell you the wall is frictionless, and then you can actually say that this vertical force is 0. That works out pretty nice when that happens. Okay. So that's what it looks like when you have the sum of the forces is 0. But we haven't dealt with the torques at all yet. And again, we've made this thing the pivot point. So that means that that's nice, because remember that because torque is going to be Rf sine of theta, at this point R is 0. So that means that the torque for both of those is 0. We don't have to add those together at all. A reminder that we're going to call all clockwise torques positive and all counterclockwise torques negative. It doesn't really matter. That's just the convention that we're choosing. Okay. Well, the tension force is going to be up. So, and we're going to give this the whole thing a length L. Okay. And this is going to be, both the bars are going to be uniformly distributed, which means that their mass is sort of centered in the middle. So we can look at the torques of those. The first, we're going to start with each force. This one doesn't have, that one doesn't have a torque either. So then we'll go to these two. Okay. Left on their own, they would make the bar actually rotate clockwise. Check to see that that's true. So it'll be minus mg L over 2. It's not going to be sine of theta because it's going to be 90 degrees between the downward force and the horizontal length of the bar. That makes it 90 degrees. And then it's going to be minus mg L over 2. Remember, it's L over 2 because the mass is concentrated in the center of an object that's uniform. Then it's going to be plus L T sine theta, and that all equals 0. Okay. And then we put all the numbers in and we solve for stuff. Okay. If you look, all these all these terms have an L, so we're going to end up dividing that out anyway. So, but the ratio matters. Okay. So we're going to end up using all that and putting it together to find those two quantities. Okay. So that's how you would solve a problem with a sign hung on a wall. Now, how about a person on a beam? Okay. This is kind of a popular problem too. So we've got, here's a beam. It's uniform. Again, it has a little mass M. And then there's a person standing on the beam. Their mass is M. And there's some distance. And then we got these things on the side. The length of the beam is L. And beam is uniform. This distance here is X2. Now let's call each of these X1, the distance to the ends. Okay. So again, you'll notice that again, I'm looking for, I'm looking to find the pivots. I want to find what I'm looking for when I solve this. So I'm going to try to find the force on each one of these points here. How much is from each one? Because they won't be equal. You can see that the one that's on the right is going to end up probably having a bigger force than the one on the left. It's got less distance between it and the person who's standing on it. So it's going to end up with a smaller force. Okay. So we can set all that up. Again, we're going to put all the forces on the beam and make those equal 0. Okay. So let's add all those up. First, let's start with just the beam itself, minus mg. Then the person, minus big mg. Then there's going to be a push from the left-hand side. and there'll be an upward push from the right-hand side. And again, that's all equal to 0. I have to write that equals 0 again. All right, now we have to find the torques of the end. And this is kind of tricky because we just have to pick one that's convenient to us. It doesn't matter which one we decide 0 is, as long as we're consistent about it. So I'm going to choose this one as 0. So that's 0. Okay, that's where we're going to measure all our torques from. Okay, so again, it's not because it's better or worse than the others, it's just because it's something. So we're going to call whatever torque goes from that 0. It actually means that we can end up solving for the one on the right, because that one's going to give us a radius of 0. So usually I try to pick the one I don't need to know. So what other forces do I have? I have this one here. Okay, and if I'm finding the distance from it, it's going to be, again, it's the downward force. If that's the pivot force, it will make it turn that way, and that is a clockwise direction, so that is a negative torque. So it's going to be negative mg, and it's going to be L over 2 minus x1. Where did I get that from? Well, L over 2 is the whole length of the beam to the middle, and then minus this little bit over here. So I took x1 and put it on there, so I subtract that off. Then I have to do the same for the person here. So that's going to be minus capital Mg. And this time that's going to be, that's kind of tricky because I have to take the distance to the person. So I know that this is x1 and this is x2. So I'm going to say L minus x2 minus 2x1. I got that because I'm subtracting this off and this off and this off to get the distance from there to there. And I've got one more thing to figure out, and that's this guy here. It's going to be a counterclockwise torque. It's an upward force, so plus F right. And again, this is kind of tricky. So it's going to be L here, and it's going to be L minus 2x1, because it's going to need to get this guy here and this guy here, but I have to take those away from the whole length of the thing. And all that put together is going to equal 0. Obviously, I'm going to be given a whole lot of numbers here. But if I know the masses and I know all these lengths, I should be able to solve for what the right force is. And then solving for the left force isn't terrible. Okay. So I wanted to walk you through the process of solving these kind of problems, and we'll look at some problems to give you a feel for what that goes like.